So to understand symbolic execution a little bit more, we've got some members from the Trail of Bits team to teach us about symbolic execution and formal verification. Formal verification is the act of proving or disproving a given property of a system using a mathematical model. Symbolic execution is one technique used for formal verification. Symbolic execution explores different paths in a program, creating a mathematical representation for each path, or more plainly, converting your code to a set of mathematical expressions. Is this the silver bullet for your auditing journey? Let's get froggy. I had the absolute pleasure of interviewing Trail of Bits head of engineering Jocelyn and security engineer from Trail of Bits as well, Troy, about fuzzing, testing methodologies, and importantly, formal verification. I have links to the full interviews with both of them in the description. And in this video, we're going to summarize a lot of that and focus on what formal verification and symbolic execution actually are. But to do that, we need a quick refresher on some of the testing methodologies that we use in Web3. If you haven't seen my invariant testing video, be sure to watch that first before coming here. And to really understand this, you do need at least a high-level understanding of Solidity as well.
What tools do we have in our toolbox to have high assurance about our program?
Layer 1, the unit test.
Obviously, you have unit tests, which you do a very specific thing like this function does this. And you start looking at things like test code coverage, like statement and branch coverage. And I think that's kind of the bare minimum.
The absolute bare minimum in security is a unit test. For example, if this is our Solidity and we have a set number function, which should set our number variable to whatever new number is, a unit test would be able to catch this. And if we're using Foundry, we could get an output that looks like this. Some assertion failed, and we can go see our test and see that when we call set number to my number, we assert that we get what we want. And if that breaks, cool, our unit tests have saved us. Foundry, Hardhat, Apeworks, Truffle, Brownie, and all the most popular frameworks have unit tests built in. Layer 2, the fuzz test.
Fuzzing is where you take random inputs and run them through your program. So you have to define things in your code that you always want to hold true.
And fuzz testing is the new bare minimum for Web3 security, because I decree. And as Troy said, you need to understand the property or invariant of your system to do fuzzing. Once you have your property defined, you throw random data at your system in order to break that property. If you find something that breaks it, you know you have an edge case that you need to refactor your code to handle. For example, if I have a function like do more math, and I know that this function should never return 0, I can throw a whole bunch of random numbers in here to try to get it to return 0. I can have a fuzz test that looks like this, which passes in a whole bunch of random numbers and tries to assert that we never get 0. And we can see from our fuzz test, it was able to pick a random number in order to break our invariant or property. Now, like I said, we recently did a video on fuzz testing or invariant testing, and I highly recommend everybody watch that video because I decree it. Foundry, Echidna, and Consensus Diligence Fuzzer are some popular fuzz testing tools. Okay, what's next? Layer 3, static analysis.
So the things that we've been discussing, unit testing and fuzz testing, are dynamic testing, which dynamic just means like you're actually doing something.
Dynamic analysis is when we run or we execute our code. In unit and fuzz tests, we do exactly this. We are running our code to try to break it. In static analysis, we just look at our code or have some tool look at our code. For example, this code here has a classic reentrancy vulnerability in our withdrawal function. If we run a static analysis tool like Slither, it'll automatically detect, hey, you have a reentrancy vulnerability. And this is great for very quickly picking out very specific parts of your code that are known to be bad practice. Some popular tools for static analysis are going to be Slither, created by the Trail of Bits team, and even the Solidity compiler could be considered a static analysis tool. So now that we have a little bit of a backstory on some of the popular layers of testing and keeping ourselves secure, let's jump into formal verification and symbolic execution now. Layer 4, formal verification.
So on a high level, formal verification is going to be the act of proving or disproving a given property of the system. This is usually done through a mathematical model of the system and the property.
There's that word again, property. You're seeing that almost no matter what you're doing in your testing, you need to understand the properties of your system. And right there, Jocelyn gave us some of the keys between fuzz testing and formal verification. Fuzz testing tries to break properties by throwing random data at your system, whereas formal verification tries to break properties using mathematical proofs. And there are many different ways to do formal verification, such as symbolic execution and abstract interpretation. For this video, we're going to focus on symbolic execution. as that's one of the most popular ways currently done in Web3.
Symbolic execution is then one of the techniques that you can use to do formal verification. Symbolic execution on a high level is going to be a technique where you are going to have your program and you're going to try to explore the different paths of the program. For every execution path, you're going to create a mathematical representation.
Additionally, if you want to learn more about symbolic execution outside of Web3, I left a link in the description to an MIT OpenCourseware video, which does a great rundown of symbolic execution. Now, let's look at Jocelyn's example of using formal verification and symbolic execution. Let's say this is our function that we want to do formal verification on, and we're going to do symbolic execution to do formal verification. Well, let's go back to what formal verification actually is. Formal verification is the act of proving or disproving a given property of a system using a mathematical model. So the first thing we need to do is figure out what we want to prove or disprove. For our demo, we should say our invariant is this should never revert. And that's what we're going to try to prove or disprove. Now, this might seem like a silly example, but you can imagine that this was a function called withdraw money, and you want users to always be able to get their money out, which would seem like a much less silly example. Symbolic execution is going to be creating a mathematical formula for this function f from our code. We're going to convert this function to a mathematical/logical representation of every execution path from our code. Once we have a set of math functions, we can push those into a solver, which will tell us if a property is true or false, or if our invariant is true or false. When we talk about the different paths of our function, we can imagine, okay, one path that our function can take is going to be a plus 1 being returned. That's going to be one of our paths. But we can also imagine that a plus 1 is actually going to overflow and therefore revert. If we pass in the maximum uint256, a plus 1 would revert. So that would be a second path that our function could take. And a symbolic execution tool would find this second path for us programmatically. And then, of course, convert these to a set of mathematical expressions. This set of mathematical expressions might look something like this: a and also not a. Imagine if you ask somebody, can this set of mathematical expressions be true at the same time? The answer would obviously be no. It is impossible for both a to be true and a to be false. This is what our solver is going to figure out for us, but with much more complicated expressions than this. In our example, the solver is known as a SAT solver or an SMT solver. And there are many different types of solvers, but I'm not going to go too deep into that right now. Running our symbolic execution tool, we would see two paths. Our first path going to be if we give it the maximum size of a uint256, we try to add 1 to it, the function will revert. Solidity doesn't allow you to add 1 to the maximum size of a uint256. The other path is anything lower than the max size of a uint256, we'll just add plus 1 and then return. So those are going to be our two paths. Path 1, a is not 2 raised to the 256 minus 1, and then a returns normally, and a is 2 raised to the 256, and it reverts. However, instead of A, B, C, not A, etc., our symbolic execution tool will give us an output that might look something like this. Now, what you're seeing on screen is an SMT lib language, and it's a language specifically made for working with these solvers to solve our mathematical representations of our code. I'm not going to go over too deeply what this is doing, but you can consider this just a list of Boolean expressions, kind of like A and not A, and if A, therefore B, and A, B, and C, etc. Now, if you take this code and paste it into a tool like Z3 or run it locally on your machine, it'll give you an output that looks something like this: SAT and SAT. This first SAT is saying they were able to find an input for path 1, and they were able to find an input for path 2. They were able to satisfy the Booleans in those different paths. Since it was able to satisfy an input for path 2, and we know that path 2 reverts, we know that this invariant is now broken, because our invariant is it must never revert, and our mathematical representation said, hey, I've mathematically proven that there is a scenario where path 2 is executed and your function reverts. So SAT here means we mathematically proved that this invariant breaks. Now, I manually created this SMT lib list with the help of ChatGPT. However, symbolic execution tools like Manticore, HEVM, and even the Solidity SMT checker can give you this SMT output. But all those tools come with a Z3 built in, so they'll even just skip this step and just give you, hey, is my invariant broken or not? Even the Solidity compiler itself can do this entire process behind the scenes. Explore the paths, convert the paths to a set of Boolean, and check to see if those paths are reachable or not. Using the Sol compiler, we can run with model checker engine, and we can look for an overflow in small sol.sol. And if we run this, you'll see the Solidity compiler was able to do symbolic execution to find out, hey, if I add the maximum unit 256 as an input to here, you're going to get an overflow, and that function is going to revert. Now, obviously, reverts are pretty easy to find, but we could even add assert a does not equal 1, rerun this, but instead of overflow, look for asserts, and we would see that, again, it was able to mathematically find an input to break our assert or our invariant. Said if you add 0, you're going to get 1. Asserts are what you're going to use if you want to use more complicated and more specific symbolic execution rather than just overflow or underflows. A tool like Manticore will also give you an output with the revert, as well as a much more hyper-specific list of S&T lib that it's inputting into its Z3 solver. So a lot of stuff just happened here. Let's recap. We built some Solidity. We understood our invariant, and the next two steps happened at the same time with Solc or Manticore. We used a symbolic execution tool like the built-in one to Solidity to create a set of Boolean expressions that represent every execution path of our code, and then we dumped them into a solver like Z3 to see if our property could be broken. Just by running this one function, Solidity was able to do all those steps behind the scenes for us. We go through a full walkthrough of this example with the interview with Jocelyn, so be sure to check that out as well if you want to learn more. And don't be afraid if this seems a little bit complicated. Be sure to ask questions, leave comments in the descriptions, and leave a like as well. And hopefully I'm going to clear this up for you.
Sometimes the solver might not be able to solve the equation too. Like if the equation is too complex, you usually provide a timeout to the solver just because if you have to invert hash function, good luck to do that with the solver.
Well, so you're saying this isn't a silver bullet for auditing? Like any technology, even formal verification and symbolic execution, abstract interpretation, these are not a one-size-fits-all approach. Using symbolic execution can run into something called the path explosion problem, where there's too many paths for a computer to explore in a reasonable amount of time, and a solver would never be able to finish.
How practical is it to take all these steps? How hard is this to really do?
So there are a couple of things to consider. The first one is that this specific technique, symbolic execution, has a couple of limitations. As you're going to explore the different paths of the program, there is a problem which is called the path explosion problem, which is basically if you have so many paths to explore in the program, it's going to take forever. If you have an infinite loop, this technique requires significant effort to be used. You need to understand how they work, and you need to understand their limitation and how to help them. And also significant effort to be maintained. At the end of the day, I think what really matters are the properties. If you want to know if a bug can occur and if the property can be broken, you don't necessarily need formal method for that, and you can use a further, which is way easier to use and provide like kind of the same type of value. Something that is sometimes difficult for people is really to understand how to create this property and how to create invariant for themselves. If someone wants to learn a bit more, we have this website. It's called securetrack.com, where we go over a lot of guidance and best practices, and among other, we have tutorial on how to use Echidna, how to define invariant, how to think about properties.
There's a high skill requirement to using these tools effectively at the moment. People are working on making them easier and easier, like the built-in Solidity SMT checker. However, as Jocelyn's been saying, sometimes a sufficiently powerful fuzzer is all you need. And if you combine a fuzzer with a symbolic execution backend, the fuzzer can pick better random numbers based off of the symbolic execution. And maybe you can find all the answers you need without having to do a formal verification test suite. And the most important piece here is that even this isn't a guarantee your code is bug-free. All it does is mathematically prove your code does that one specific thing correctly. I'm hoping as AI takes off, doing a lot of this will become much easier, and I guess we'll have to see. But for now, hopefully you learned at least the basics of symbolic execution. If you'd like to learn more, leave a comment in the description. If you want to see more videos about formal verification, let me know. But the takeaway from this is that you should become a stateful fuzzing wizard. Thanks all for watching. Be absolutely sure to go watch the interview with Troy and Jocelyn, links in the description. And we'll see you next time.